periodic function is something that has the following property. F of x, which you should remember what this means. This means the y value at x. So for example, if you went to ask for the f of 2, then f of 2 is equal to the y value when x equals 2. And if you ask for f of 4, that'd be the y value when x equals 4. A periodic function has the following property, that the y value at x is the same thing as the y value at x plus p, where p is just a number. Oops, hold on a second. Okay? Now, at first, you might say, well, that doesn't make me feel good about what a periodic function is. But you actually know an example of a few periodic functions. Here's some examples. So let me show you one that's pretty famous. The sine of x is the same thing as the sine of x plus 2 pi. Okay? Now, maybe you're not surprised with this. You know sine x is a periodic function. And why is that? Well, when you graph it, it does the following. It goes up, down, comes around. This is the number 2 pi. This is the graph of y equals sine x. Okay, here's some special numbers. Here's pi over 2, pi, 3 pi over 2. Goes through a max height of 1 and a minimum height of -1. Okay? And then it continues. So we know the graph starts the same pattern. I'm going to draw the next cycle of this graph in a different color. So it looks like this. Okay? And the following fact is true, that this y value here, so this y value is equal to f of pi over 2, which is actually equal to 1, is the same as this y value over here, which is exactly 2 pi away from there. Okay? And what's fun is that this thing holds true for any x value. So what that means is, like, if we pick this x value here, and we go forward amount of 2 pi, we land on a new x value. So whatever this x value is, I don't know what it is. Let's just call it, we'll call it a. This number is a plus 2 pi. And that's what makes this function periodic. About that, this point here has coordinates a comma sine of a. That's what it has. And over here, this point has coordinates a plus 2 pi comma sine of a plus 2 pi. And you can tell, look, the y value at those 2 points, if we trace back to the y-axis, is the same thing. Okay? But a function's only periodic if this idea works, this idea that the sine of x is equal to the sine of x plus 2 pi for every x value you can dream of. Okay. Now, here's a fun little fact. Suppose I'm thinking of a function and I say, draw f of x such that f of x is equal to f of x plus 2 pi. So the question I'm going to ask is, do you have to draw y equals sine x? Are there other functions? Okay, one example is y equals cosine x. That graph has the same period. It takes until 2 pi to repeat itself. Then you get a copy of the original graph again. So that could be one thing, y equals cosine x. But it doesn't even have to be a trig function. It just has to be a function where this idea holds true. So watch. So I'm going to make this function. The function does the following. Here's 2 pi out here. And let's pretend it's like this. It's a line segment starting at 0, 0. And it goes up to a height of 1. Okay? And if I want this fact to be true, that f of x is equal to f of x plus 2 pi, then I need to get a copy of this thing for the next 2 pi of distance along the x-axis. So here we go. So this is an example of a periodic function that satisfies that condition, and it's not a trig function. I have one little criticism of this thing. Thank you. I need to be careful because the way I've drawn this, it doesn't pass the vertical line test at this point. So I just need to fix that, but I can do that quickly. I'm going to take these 2 points up here and make them hollow. So if we make them hollow, then this thing would be a function, right? And it's still periodic with we say periodicity 2 pi, fancy word, how long it takes before it repeats itself. So let's look at a few graphs and see if we think that they represent periodic functions. So consider a graph that looks like this. Okay, so you have some graph that looks like this, and the question is this function periodic? So is it true that f of x, the y value at an x value, the y value at some particular x value, is equal to the same y value p units later, whatever p is? All right, so let's say I go to the top of this over here, right? Got it? And if I look across on the function for another point where that y value is the same, I find one over here, right? So if this thing's going to be periodic, it would have to have that distance as its period. Okay? But that doesn't work, because now let's say I go to this point, and I go across a distance of p, and then I look at this point here, and this point is not on the graph. So this fact down here is not holding. Now it's tempting to look at this and say, hey, look, but it's like a wave. It goes up and down, up and down, up and down, right? But this doesn't hold, because no matter what we add, we can't pick one number to add every time, where if we shift to the right by that much, we'd always get the same y value. So this thing's not periodic. It's tempting to think it is at first. Okay? So let's go to like a Ferris wheel type problem and look at and keep this idea of what a periodic function is in mind. So let's consider this graph for a minute. All right, so it starts at 20. It looks like it's going to go down to a height of 5 and up to a height of 35. And we've got a midline going through the center of the graph like this. There's a midline, y equals 20. And the graph itself does this. It goes up, down, back up, and then it does it again, up, down, and back up. And then it does it a little bit more. It goes up and down. They labeled this point here as a 7. So the question is this function, first off, let's start, is this function periodic? Is it true that we can complete this statement? F of x is equal to f of x plus p for some number p. Okay? Well, if you look at this part of the graph here, there is one complete cycle, right? So it looks like a sine curve. And then if we look here, there's a second cycle. Here's what we need to know. We need to know the amount of time before this graph repeats, and that would correspond to this x value right here. Whatever that is, that's what it takes to get one whole period done. So if I can figure out that distance, which I'm going to call p, that will be the number I'll put here, and then I'll know what the periodicity of this function is, right? So if we give it a little bit of thought, though, we can see, I'm going to trace over this now. If you look at this piece of the graph we have, and I stop right there, you should ask yourself, how many complete curves did we get between 0 and 7? So let's count up. We've got one curve to here, and then we have a quarter of a curve, another quarter of a curve, and another quarter of a curve. So it looks like we have 1 3/4 of a curve, and that's equal to a distance of 7. Right? So I'm going to call this 1 3/4 curve. I'm going to say the period of the curve, 1 3/4, which I can think of as 7/4. So 7/4 of the period is equal to 7. So the period of the graph must be 4. We can say then that this function satisfies the following rule, that f of x is equal to f of x plus 4. All right. So now that we know that, we could actually go ahead if we want and find the equation of this Ferris wheel, and we know all the facts. So it looks like it takes 1 minute to finish a revolution. And actually, this is sort of fun. We're going to actually draw the Ferris wheel based on the graph of the Ferris wheel. That's sort of fun to think about. Okay, so here it is. Let me just put my axes back. I didn't copy them. Okay, so this is x equals 4. So our Ferris wheel looks like this. And if we think about it, the midline was 20. So I'm going to draw in the midline of the Ferris wheel like this. And what we know is the distance between the midline and the ground is 20. Right? And then we know, if we look at this graph, the amplitude of this graph is 15. This graph goes 15 above its midline and 15 below its midline. So that means the radius of the Ferris wheel is 15. Okay? And then now we know that the distance above the ground must have been 5. Okay. So now we need to figure out where we are at different times. So at time 0, we're at a height of 20. So actually, we can start here, right, or here. It doesn't matter. So say we start here. We'll call this t equals 0. And what you notice is that this graph goes up to a height of 35 by the next important time. So up here is going to be t equals 1/4 of the period, because I've gone 1/4 of the way around the Ferris wheel. It takes 4 minutes to do that, so this must be t equals 1. This must be t equals 2. This must be t equals 3. And then we're back to 4 again. So we can tell clearly by looking at our graph that it's a sine graph. So it's going to be h of t equals blank sine a blank, some number times t plus the midline. Well, the midline's 20. The amplitude's 15. And then we needed to know the period of the graph, but we figured that out, that the period of the graph is equal to 4. So then 4 equals 2 pi over b. So if I cross multiply, I get 4b equals 2 pi. B equals pi over 2. So then that goes here. And what you have now is the equation of that Ferris wheel. So let's switch gears a little bit. And this is about finding exact values of trig functions. Okay? So switching gears a little bit. So let's consider an example. Suppose you're told that the secant of theta is equal to 17. And then they ask you for things like, what's the sine of theta? Or what's the tangent of theta? Okay. So a good way to start this, first off, we're also told that theta is between 0 and pi over 2. That helps a little bit because you don't have to worry about being in the second or third quadrant. You're not going to have any negative or positive values. It's just all going to be positive. Okay. So let's take this fact. Secant is really 1 over cosine of theta. So we know 1 over cosine of theta is 17. Well, if you cross multiply and solve cosine theta, you get cosine of theta equals 1 over 17. Just flip both sides of that equation, and that's what you get. All right. So I need to find these things over here. Let's draw a triangle. We know we can do that because the angle theta is between 0 and pi over 2. And so if I put theta in this corner, that would be okay. That's a legitimate triangle. The angle's not too big, right? And we know the cosine of theta is 1/17. Well, cosine is adjacent over hypotenuse. So this is 1, and that's 17. Okay? So with a little bit of work, we can get this side, right? Let's call that missing side b. 1 squared plus b squared equals 17 squared. 1 plus b squared equals 289. And then b squared equals 288, or b equals the square root of 288. Now, if you want, you can reduce that. That is the square root of 144 times the square root of 2, or 12 rad 2. So now I know the missing side of that triangle. I can go put that up here. 12 rad 2. And then finding these things is not going to be so bad. So, for example, the sine of theta would be opposite 12 rad 2 over hypotenuse 17. The tangent of theta would be opposite over adjacent, but that would be 12 rad 2 over 1, or just 12 rad 2. A new page here. And consider this question. The secant of negative pi over 6. Let's see when I find the exact value of this thing. All right, so some people might be more comfortable if this was in degrees. Well, pi radians is 180 degrees, so we could just do 180 over 6 and get 30 degrees. So we're asking for the secant of 30 degrees. We need to be careful. It's negative, though. Okay? So let's draw that. Okay? So negative 30 degrees means we'd land in the fourth quadrant. Okay? All right, let's remind ourselves what secant is. Secant is really 1 over the cosine of negative 30 degrees. So our plan is going to be figure out what the cosine of negative 30 degrees is, whatever that is, and then we'll take the reciprocal of it. 1 over it means we're going to flip it, see what happens. Okay, so the cosine of 30 degrees, right, we actually know. The cosine of 30 degrees, right, would be 3 over 2. Now, why am I asking that question? Well, the reference angle, the angle this thing makes with the x-axis, is 30. So it's going to have the same absolute value as the cosine of 30. However, we need to ask ourselves, is it going to be positive or negative? Well, we know this little trick, right? All students take calculus. The C means that cosine's positive in the fourth quadrant. So the answer to the cosine of negative 30 is also positive rad 3 over 2. Because it's positive, cosine's positive in the third or fourth quadrant, that is. For those of you who don't remember it that way, the other way to remember it is, don't forget, if we're on the unit circle, that the x value is always cosine of theta and the y value is always sine of theta. So if you were in the fourth quadrant, your x value, cosine theta, would be positive. Okay? So that's how you know. All right. Well, to finish this up, we just do 1 over rad 3 over 2. That's 2 over rad 3. Now, that's an acceptable answer. Most of the time, you've been trained to rationalize denominators. If you want to do that, multiply top and bottom by rad 3 over rad 3. You get 2 rad 3 over 3. All right, so let's do this. Again, it's probably convenient to switch this thing into degrees. Okay? So if you replace pi radians with 180 degrees, you'll get cosecant of 225. Okay? Cosecant is 1 over the sine of 225. So we're going to draw what 225 degrees looks like and figure that out. 225 would land here in this quadrant. Okay? The reference angle, the angle that thing makes with the x-axis, is 45 degrees. So what that means is that the sine of 225 is equal to the sine of 45 up to an SIG end. So you have to check if it's going to be positive or negative. Right? But in the third quadrant, the only thing that's positive is tangent. Sine and cosine are negative, so there's a negative here. So now we know our answer is negative rad 2 over 2. Okay, well, our answer at least to negative sine 45. Okay, that value needs to get plugged in here, and then we can finish the problem. So we get 1 over negative rad 2 over 2, which is negative 2 over rad 2. Multiply top and bottom by rad 2. Get negative 2 rad 2 over 2. Well, that's sort of fun, which is just negative rad 2.